It's super easy, and there's no tuning, there's no complications. Imaging is very fast, and you can always obtain a frictional force image, which provide material property, and you can do force curve. Force curve, remember, it's in contact mode because you're measuring force versus distance. And it's much better for sample with very tall features and sharp edges because that contact mode can follow the tall features much faster than tapping mode in some cases. The disadvantage is that when we're imaging samples that were disturbed by the lateral force, for example, soft materials, the contact mode will actually cause a problem on these imaging, these samples. And then tip sample could also be easily damaged because of vertical forces, because the tip is actually dragging on the surface. And if the sample is very soft, it could cause damage to each other. And later we'll talk about how do we overcome these problems. Okay, so contact mode feedback. Here is a slides collection put together by Steve, and he sent me this slides a couple of weeks ago. So that's great, very well put together. And here we have a laser that shines on the back of the cantilever and then bounce into the detector. The detector outputs signal into the feedback electronics, and the feedback electronics will collect the deflection signal, which is the force signal, and then compare the signal with what we call the set point. Set point is a set point of force. And then the difference between these two signals generate what we call error. Error is the difference between your detected force versus the set point force. And if there is a negative force, and then deflection come out, will feed back into the Z. Therefore, to try to make the tip and sample in constant contact, and the feedback signal come back, plot into the image. This is your topography image source. And then the residual deflection signal is output as a deflection signal. So that's the feedback of contact. There's no oscillation, there's no tuning, very simple. Okay, so cantilever we use a deflection type of cantilever to sense this force. So you have a laser point at the back of the cantilever, and as the cantilever push into the sample, the force between tip and sample cause the reflective light here, in this case light, to bounce up and down. And this bounce up and down tells you how much force it is. If you have more repulsive force, the deflection, the dot will become higher. And if you have the attractive force, the deflection signal will be lower. Simple as that. Okay. Deflection signal set point. Here, when you turn the instrument software into a contact mode, you will notice that this green crosshair and your laser dot, and there's always a yellow dotted line. When you see this yellow dotted line, it is indication that your software is working under a contact mode. If you don't see the yellow dotted line, the instrument software is working under tapping mode. So this is an indication. And it's also a reminder to tell you that you want to adjust your detector so that the deflection signal is slightly negative. The reason is to just as a convenience that if you at the beginning of default settings, the set point is always set at 0 volts. And then if you want to have a good proper approach, the deflection signal always need to be slightly negative. Okay, so this yellow dot line has two things. One is to remind you that it is in contact mode. Two is to remind you that you need to adjust your detector so your deflection signal before the tip and sample contact is going to be slightly negative. Okay. It is perfectly fine for you to put the set point to be positive and then the red dot into the center. You can do that too. As long as your set point is higher than your deflection signal, it's going to work. But this is just a convenient reminder. Okay. Here, deflection set point. Use at the same set point, different initiate deflection. At the beginning, you should adjust the detector so that red dot is slightly below the horizon. And then so after you approach that, the red dot will jump higher, and then the feedback will kick in, and therefore the adjust the Z height of the scanner, and therefore at when feedback is in and tip is in range of the Z range, your deflection signal will match the set point. And if your set point is 0, your deflection signal should be 0. Okay. Yes, here this slide says why must the set point be more positive value than the initial deflection? That's because you want to put the tip and sample in contact. You have to make sure that before the contact, the force is slightly below the set point. That's what it's about. It's perfectly work fine when your deflection is 5 volts and then you put the set point is slightly higher than 5. That's fine. But if you put the set point slightly below the initial deflection, then if you click this approach, the approach will stop because the feedback will consider that tip and sample is already in range, and then it will refuse to approach. So if you click the approach button and the green bar turns red and then the approach immediately stop, that's because your set point is below your initial deflection. Okay, so once you have this done and it's time for you to bring the tip close to sample and only, this is called initial approach. So I always tell people that when you finish the previous days of AFM work, you should always do a big withdrawal, basically bring the sample height away from the tip. So next time when you put a sample on, the sample does not crash your tip, okay? So in other words, the next day when you start a new days of work, you should try to bring the gap to be smaller. That's because the automatic approach is relatively slow. Okay, it's rather slow. So if you do automatic approach, it takes a long time and it's not convenient. So you should use the switch at the front of the head electronics box to bring the sample close to the tip before you do automatic approach. You should move. And there's a lot of adjustment that you can do. And at the end of this presentation, I will show you a small trick to visualize the tip sample distance. So during contact mode, you always need to open 3 channels, typical 3 channels. One is topography, in which tell you the height image, and you always have a deflection. Deflection signal is actually from the arrow signal. That's mathematically the topography is the integration of deflection. In other words, deflection is the first order derivative of topography. So it is a slope image. It will appear to be sharper. And then when you have very small features, the small sharpness is very nice. And then you always have to have a frictional force imaging, which record the twist motion of the cantilever. This records the friction between tip and sample. And some people also call this a chemical force microscopy. So it shows you the chemical bonding between the end of your cantilever tip and your sample. Okay. So that's three channels. In the center is topography. The one on the left is friction. And remember, frictional force imaging always has two channels. One is scan left to right. The other is right to left. Or we could trace and retrace. And then these two is always opposite to each other. And then the difference between these two is actually the frictional force. Okay. Okay, here's the pre-engage checkup. First, you set the mode to contact mode, and then you choose the correct calibration file. If you don't choose the correct calibration file, your distance measured is not correct. And then you verify the servo settings window, and then double check the photo detector alignment, which I said before that you align the photo detector so the signal is slightly negative. And then you check the proper set point. At the beginning set point, normally we'll put the 0, and then you will do an approach, check the approach speed. And then when we do contact mode, I normally put the speed as maximum. And then you adjust the tip sample separation distance using the video system. This is what you call the rough approach, and select scan size, resolution, and then click approach. That's your checklist. Contact mode pre-engage check-in. Servo typical value shown here on the right hand side. Oh yeah, check the IP again. The initial number is always 3 and 3, and 3 is somewhere not too high, not too low, and actually from 1 to 3, it's all work. If it is above 10, there's a chance that after the engage, your gain, I gain is too high. Where your I gain is too high, you send the scanner into oscillation, which sometimes when you do it for too long, it will harm the piezo in the scanner. P gain, actually, I see that's not quite sensitive to anything. I just leave it some numbers and make sure the set point 0 and so on and so forth. Bias, we don't have any bias here. We don't do connection here. And then range should be maximum. If the range is very small, you type a very big number, you set at the maximum. Sample bias is the voltage you put on sample, and this is only useful when you do, let's say, conductive AFM. Okay, so when you click the scanner and scanner motion window, and you put the stop at value at 0, which in this case basically is when the deflection is changing from your initial negative several volts or several like 1 to 2 volt to 0, the approach will stop. And here is the approach speed. Here is set at 1.2. I always like to have a little bit higher, unless you want to very carefully protect the tip sharpness. And then in a liquid environment, so on and so forth, you can set up lower. And then you can click approach, I think. Here is the summary of contact mode initial settings. Some signal is typically greater than 1.0 volts. If it is smaller than 1.0, check your detector. And then your detector has 4 dip switches on it. You look carefully. When that 4 dip switches are up, it is actually at low gain, and when the dip switch is low down, it is a high gain. And then if the signal is too low, maybe your dip switch is at the wrong settings. You should switch it so that some signal need to be greater than 1 volt. And then you set the deflection, initial deflection on HEB slightly negative, in this case, negative 1 volt, so on and so forth. And then you need to adjust the detector so your frictional force image, frictional force signal is around 0. Set point 0. Speed, scan speed, initial speed, IP gain 2 to 3, 256. And then after you check these, it's good to go. And here's the button show you the approach, approach and withdraw. Here, in your instrumentation, your approach is actually move the sample close to the tip, but in here it shows a red arrow shows the tip into the sample. Basically, it's just a logo shows you this is the approach button. You click that, it'll approach. And on the right hand of the approach button, there is this one red arrow, which is a withdraw button. And here on the scan motor window, there is a withdraw 20 micron setting here. Okay, so this is when you click once, it will withdraw 20 micron. And this 20 micron is good for you to withdraw and then go to next area and then approach again, because 20 micron make sure the tip is safe away from the sample when you move the sample around. But at the end of the day, I normally put this withdraw a much higher distance. So you withdraw a long distance. Next time when you put the sample on, it'll reduce the chance to crash the tip. The one on the left to right logo here on 3, this is the scan button. Click that, it'll open your scan window or and your laser indication window. That's your scan button. Okay, there's a couple windows I want you to pay attention to. Here on the upper corner, this is the arrow signal or oscilloscope. This oscilloscope is important because that will show you what's the noise level when tip and sample is not scanning, and or your gain is it too high or too low. When the gain is too high, you will see a very wide oscillation, and this oscillation will show you the oscillation that indicates your gain is a bit too high. Okay, so on a servo window after approach, you will see this little green bar here, and this is very important. This green bar, when it is on, when it shows green, and there's a yellow line here, that means that your high voltage is on. It means that tip of sample is approached, it's engaged, And then the yellow line shows where does it engage versus in the range of the Z. When you have a big drift, for example, your sample has become taller or your sample is too close to the tip, too close, and then also range, this yellow line is higher. When your sample is too far away from your scanner, this yellow line is lower. It's possible that this yellow line will continue to drift until it is so low that the yellow line doesn't show anymore. That means your sample is way too far. Okay, this is possible. And it's also possible that yellow line will drift higher until the entire green line turns into a red line. Okay, that means either you crashed or entire approach is not correct because your set point is below your free deflection, and that this yellow line is also very high. So when you see this yellow green bar with yellow line approximately in the middle, that's indication that your tip sample is engaged and it's in range, you're ready to scan. There you go. So false engaged, that this is when tip and sample, when the approach stop and this yellow line is very much below, that means tip is not even touched the sample. So it's indication that you're actually not engaged. It's a false engage. And then you can see the deflection still is negative and tip is away from the sample. And then this deflection signal is still your initial deflection signal. Approach did not cause the tip to engage the sample. And here you see this red line on the right. That means the tip is pulled all the way back, and the Z piezo fully retracted. And then if you look at the deflection signal, if it's very high, it's possible that you crashed, or your set point is here. In the set point is -3. It means that your deflection still is above the set point. So the software interpret that the tip and sample has crashed. Okay, later on my computer, I will simulate all these situations and then we'll see what happened there. Okay, so here, and I just said that before, that when tip and sample engage, it is still possible tip and sample did not engage right in the middle of your Z range. It is possible your sample is too far away from the tip, from the scanner, or sample is too close to the scanner. It's possible. Okay, you could actually correct that by step the sample away from the tip or step the sample into the tip to make this yellow line in the middle. And this is actually can be handled by two different ways. Here is the way is that on your scan and motor window, there are two buttons here. It's called step close and step open. Step close and step open, when you click that, it's actually rotate your approach motor one step. Okay, just one step. When you click that, it will do approach or withdraw one step. This will fine tune your tip and sample distance, basically make the sample higher or lower to correct height of the sample. In this case, we could click this close a couple of times until the yellow line is approached to the middle. Okay, it's just going to fine adjustment. Okay, and after you adjust the height of the sample, and this two buttons pop out on the scan window. Here it's scan, and these two pop out when your software is ready to scan. And there's two buttons. One scan the scan from top down, the other scan from bottom up. Okay, and here there's another interesting, useful thing. It's called frames. Here you see a infinite, and there's a 1 and infinite. Okay, this is how many times you wanted to scan. If you click 1, it will scan once and stop. And you can check this box, say withdraw when done. That's if you want to scan, and then at the end of scan, you withdraw the sample. That's why you check this box. But if you want to continue scan, non-stop, you check the infinite. And therefore the scan will go in back and forth scan. And when you finish a frame, it'll continue scan the next frame. Here you have scan size. Its unit is micron. Offset shows you where you want to put this frame. Speed here is ln per second, that's line per second or hertz, and points. This is pixel number 512 by 512. And then typically you can also do 256 by 256. Angle here shows that you can rotate the scan angle. And why do you want to rotate scan angle? Sometimes the scan show you a better image when there's a step, when you scan across the step instead of parallel to the step. So you can rotate your scan angle. Okay. Here is a couple of optimization you can use to optimize your contact mode. The one of the adjustment often do is the IP gain, I gain and P gain. Here we set 1 and 1. Typically, you need to have this number a little bit higher than that. And we already talked about set point, sample bias. Here there's a 1 volt of sample bias, and then allow you to apply a 1 volts of voltage to your sample. Range is you could actually reduce or increase range up to your maximum range of your scanner. And reduce the range help to increase your Z resolution. Okay, optimizing steps to the contact mode. There's 3 parameters you can adjust to optimizing: set point, which will increase or decrease your force; scan speed; and servo gain. Scan speed, how fast you can scan; and then servo gain, determining how sensitive your feedback loop to the response of topography. Okay. So you could using a couple of tools to help you to adjust, to optimize. One of the tools is called the real-time cross, that you can turn it on. Later I'll show you. And then using the real time, you can optimize scan speed and then servo gain, and then servo IP gain, and to make your topography to the best quality. I'll show you when we have time today. Here is a example of that. Your servo gain is too high. Your servo gain indicates how sensitive is your feedback to the topography. And of course, you want to be as sensitive as possible. However, when it's too sensitive, it generates oscillation. Okay, so this oscillation can be seen on the baselines of deflections and topography. And then when you see this oscillation, you need to reduce your servo gain until the oscillation disappear, and it reduce a little bit more to make the servo gain into more stable region. Okay, so here's some key points of contact mode. Feedback loops works keep cantilever deflection constant by applying a voltage to Z piezo. Topography equal to the voltage applied to the Z piezo times calibration factor of the piezo. Basically, it's the moving path of the cantilever driven by the scanner. And then the initial deflection after approach is determined by the difference between deflection settings before approach and the set point defined by user in software. Liquid cells, and there is contact mode. There is one biggest problem of contact mode to prevent it from achieve very high resolution, which is we call the capillary force. When we do a force curve, the tip and sample always have a very strong attractive force. This attractive force will snap the tip to the sample and then generate initial force. This force is sometimes very high. And that's why contact mode does not achieve the best resolution, because the force is always slightly too high. By adding imaging in liquid, you can actually reduce this force, because when you're imaging totally in liquid, your initial, caliber force is actually 0. And you can fine tune your set point so your force is near 0. When the force is near 0, you protect the tip and protect your sample and achieve very good resolution. This is the original design of the liquid cell. We can see the couple of clips and an O-ring and the plastic piece, which is allow you to fix a piece of mica or your sample substrate to your sample stage. I will not go too much into detail into liquid cell because liquid imaging is totally different topic. So I like to break it down to a complete different presentation in the future. And I'm going to fast forward to here, this part. Okay. The reason I put this is to tell you one of the things about contact mode is that you could actually using contact mode to achieve very high resolution. It's actually some of the very high resolution images that I did is actually in contact mode. The graphics on the left is a force curve of your contact mode. And you can see there's a big sharp drag force here. This is the capillary force. This is the initial force the tip and sample attract to each other. And this force is always there. So that's why when you do contact mode using a soft tip, even very soft tip on a soft sample, the image is very bad. That's because tip is always attracted to sample with a strong force. You could eliminate that force by imaging in fluid. When you do force curve in fluid, this force has disappeared. So you can fine tune the set point so the tip and sample is barely contact with a minimum force. When you do that, your tip and sample has a very, very small force attract to each other. And very small force will protect the sharpness of the tip and the original shape of the sample. You can achieve very high resolution. This is a contact mode image on a self-exam monolayer of thiol. And this self-exam monolayer of thiol cannot achieve this resolution when you do tapping mode because this is a very soft sample. It is basically all the organic molecules standing up and line up on the surface. And you can only achieve this good resolution when you image in ethanol using contact mode with a fresh, sharp new tip. It's only that's possible. Okay. And this is a zoom in on one of the samples, and this is a 40 nanometer scan. You can see the alignment of these molecules. And then you can see this line by line. This is a molecular resolution of this self-exam monolayer, C18 self-exam monolayer, and it was achieved in contact mode in a very clean tip, and then at very small force by fine-tune the set point. Here in contact mode, higher set point means higher force, lower set point means lower force. If your set point is below your initial deflection, your force is 0. And then you have to set the set point so it is slightly higher than your initial deflection. Therefore, your force is minimal. And here's another example of the same sample. When you zoom into, here is 20 by 20 nanometers, you can actually resolve the molecular lattice of this particular sample. Another advantage of contact mode is that you can actually scan very fast in contact mode, even you are using not very high-end electronics. You could actually do what you call a constant height mode. Basically, you are not depending on the feedback instead of you depending on the deflection signal to resolve the topography. When you use a soft tip, the force is not very high, and therefore it allow you to scan real fast. And these images are scanned on upper left corner. This is the calcite in water in regular contact mode. I gain is 30. And on the lower corner, this is the constant height mode. I'm scanning 15 lines per second, which is very fast. I gain is set 0.01. So I'm not using the feedback to resolve the atomic step. I'm just using the deflection to resolve it. And here's another example of using contact mode, and you can scan relatively fast and you can resolve molecules. Even these molecules are very soft. This is again self-exam monolayer. It self-example on the surface in ethanol, and you can see the chemical reaction happen in real time. And some forecast. In June 6th, we're going to have Igor Sokolov to give us talk on his ringing mode. I have not nailed down the presentation time of the other professors I invited yet. Just tune in. Thank you for your time. I can use some questions. At the same time, I'm going to switch the camera. I will show you something that's a little bit different. Thank you. You can ask your question at this moment as I try to do something else. Go ahead. Okay, if you don't have questions, what I'm going to show you right now is this little device I use to help with the optical microscope with the instrument. Okay, so let's look at the camera here. Stop sharing the PPT. Okay, today I'm bringing in this little device. It's quite cheap. You can buy them from Home Depot. Just a light. You can turn it on. Okay, what can you do with this light? I'm going to show you where do I put it. Let's see if I can switch to Nikon. Okay, you put, first you remove a sample. You can put underneath your sample right here and let it point up. Okay, let me turn on my, turn on the other computer, see if I can show you. Okay, what I'm trying to do is turn on the Zoom share on the other computer, which drive the instrument. Oh, it asked me to update, so it's going to be a couple of minutes. And then let's see if I can do this. A couple more minutes. So let me talk about one of the drawback of this particular design, the scanner. And this scanner, this is the Agilent airframe scanner. Let me show you. There's another scanner here. And this scanner has an integrated optical microscope through the center of the scanner, right? It's a tube, it's a light tube. Okay. It is very convenient because you look through the scanner, look through the center of the scanner, you see the tip. Okay, it's very clever design. Right. But there is one problem when we integrate the optical lens into a thin tube. This little tube is too small. It's very small. If we are familiar with the optics or cameras, whatever, if you're familiar with camera, one of the problem of this you can immediately see is that it has a very small numeric aperture. So if you're using a camera lens with very small numeric aperture, it does not collect enough lights. In other words, the image is very grainy. So that's the reason that even the Agilent AFM using a very good camera, it still show you a grainy picture. Okay, and then this grainy picture basically make it very difficult to see, anything if your sample is not shiny or does not have a lot of lights. Okay, so your picture is not very good if your sample is not very shiny. Okay, so and then when your picture is not very shiny, when the sample is basically not a reflective, it's very difficult to see. And also it's very hard to see your tip when there's no reflective sample there. That's also another possibility. There's difficulty. However, you can put a light underneath your sample to add extra light. So you use a transmission light. Okay. So what does it do with transmission light? Let me show you. I'm going to share the screen on that computer, and then hopefully I can show you this. Hit that host. Yes. Okay. Now I'm going to share the this guy. Okay, now we are looking at my computer that controls the instrument. And if I turn on the light here, Yeah, you don't see a lot of things. It's very dark. Try to turn this on. There's too many windows here. Okay, here it is. Control. Camera view. There's something wrong with the this. Oh, here it is. Okay. Okay, so this is what you see. You barely can see anything. And if you turn the light, you can barely see anything. We're actually looked through the scanner and into the tip. This little red dot, I think that's the laser. Yeah, see that I turn off the laser, the red dot disappears, so that's the laser. So even we are looking at it, because there's nothing reflective underneath it, it's very hard to see anything. Very difficult. However, if we turn on the light underneath, you can look at the camera here. I'm turning on the light underneath it. Now you can see the tip. Okay, this is very convenient. That's because that you could fine-tune tip sample distance. This only works when the sample is transparent. It does not work when sample is opaque anymore. You can move your lights around to adjust the brightness, right? And you can see the laser and your light at the same time. So that's a little trick, help you to visualize your tip. Let's see if I zoom in to see how good is the resolution. Yeah, you can zoom in and you can see that the image quality is quite good. And when you zoom all the way in, you can almost see the tip. It's a little bit on the side. A little focus. Okay, you can kind of barely see the tip itself. And this tip, we know that it is about 5 by 5 microns square. So your resolution is about 5 microns. That's which is good. 5 microns, you can kind of almost see a piece of like E. coli bacteria or grain of starch. Yeah. There you go. So with the help of a transmission light, you can improve the optical image a lot. Okay, so just one trick you could do. Okay, so now I'm going to put a sample on because my sample is opaque and this technique no longer works. It only works with transparent sample. Let me close this. Okay, so this is already pre-adjusted. The zero, the frictional force a little bit. Oops. Or adjust so that it's close to center and slightly negative. Okay, the deflection negative 1.5. And then I'm going to put a sample and ready to approach. Approach. Some of the cable is not attached. Okay, now the approach stopped, and you can see the green line here, green bar. It shows a yellow line somewhere in the middle. I'll show you a little bit about the step open, step approach. Here, it's actually in the step motor, and then you can activate all the motors or activate one motor at a time. And when we do a fine approach, I'll normally choose one of the three motors, right, left, or rear. Click that, and you see this, the yellow line is slightly too high. I'm going to click open a couple of times. Open, open. See that? Immediately move the sample lower a couple of notch. And then I like to have the yellow line slightly lower than the horizon instead of above. That's because they give you more room if the sample happen to be very tall. And then you go to the servo. It's 20 already. I should put it lower. Yeah, because I see a little bit noise. And I'm going to go to 10. And we're ready to scan. Here, I'm going to do 2 lines per second. 256 and scan. We could use the real time to look at the signal. And then fine tune the I gain and P gain here. Here, when my gain is too low, let me put it at 1. You can see the topography become blurry. And then your deflection become more clear. Let me turn this on. Now your deflection appear to look like topography. That's the constant height mode we just talked about. And topography image looks blurry. And if we increase the gain to 10, then we got to increase a little bit more to simulate when the gain is too high. Let's see, where's the oscilloscope? I can turn it on. Yeah, this is oscilloscope. This isn't. Lower this. Close this. Put oscilloscopes here. So I'm going to increase your gain and look at the oscilloscope. So when you're scanning, when the oscilloscope show a little bit up and down, which is normal, this is your signal. It's not noise. That's 26. This is a very good scanner. This scanner, it's kind of very difficult to make it into oscillation. It's 40 already. Yeah, this scanner is so good. 46. I cannot make it to oscillation. Sorry. So yeah.
Hey, Song, open your scanner calibration file.
Hold on, give me a second. What am I looking at?
That's your scanner calibration file. Do you see on the right-hand side servo gain multiplier 1.0?
Oh yeah, yes. Hold on, where's it? When I'm looking at? So, oh, okay,
right
yes,
there.
1.0. Yeah, yeah.
Before you change that, reduce your I gain back to 20 and then change that to 5.
So 20. Should I go further lower just in case?
That's your call. If it starts screaming at you, you need to react.
And then we'll hear it. Let's go to, oh, you get a 5. Does it immediately come into effect?
Yes.
Okay.
All right, now try and get it to oscillate.
All right. 10. Increase. 12. Oops.
There you
now
go.
We hear it. Yeah, yeah. Okay. Yeah. So even at 18, yeah, you see this is noise. And I'm going to lower to kill the noise. Now the noise disappeared. And then lower a little bit further just to increase some stability. And that will be it. Let me see what else. I'm going to do a couple of force curve. I don't remember I did force curve last time. Let's do stop scan. And then force curve is this thing, force curve. This is the force curve window. Here, duration, that's the speed you're doing force curve. I'm going to put on 1 data points, 1000. Start end. Let's just do 1 so we see what it look like. Force curve. Oops, that's a full range. I think a little bit too far or too close. Wait. Let's do another one. Range is too low. Simone? Okay, that's a force curve. So that's a maximum range force curve. And this is the attractive force that we're looking at. And then when we do real force curve, you don't want to do full range. You always put a little limitation here. Let's do a max limitation. Let's put 2 volts on it. And force curve. So basically when the deflection reaches 2 volts, the force curve, the scanner no longer push into the sample, it'll reverse and then finish the entire force curve. This big chunk thing, that is an attractive force between tip and sample, we call it capillary force. And that's about it. If you have any question, please unmute yourself and ask us. Steve, do you want to cover some of the things you want to cover, like drifting and so on and so forth?
Well, we're kind of running short on time at this point, but one thing we can do is kind of demonstrate what detector drift looks like if you'd like.
Sure, yeah.
So the first thing that you would need to do is realign your laser. So
I'm gonna
right
withdraw.
now,
Yeah, I'm gonna withdraw right now.
so right now you've got your laser aiming at one of the cantilever tips.
Yes.
What you'll want to do is you'll want to move that and reflect it directly off of the substrate rather than the cantilever.
You want to move the laser away from the cantilever?
So right now it's reflecting off of the cantilever.
Yes, that's right. Yeah.
Reflected off of the substrate the cantilever is attached to.
Substrate, the chip. Okay. Let me look at the camera. Do you want me to remove the sample?
You don't need to if you don't want to.
This way you can see it much better with the optical microscope. So we can see it. Where's camera?
Top.
There you go. Okay. So I move the laser into the substrate. How do I do this? Oh, here it is. Hard to see.
What are you? There you go.
There you go. Okay.
Your camera didn't show you moving it. You must be moving on a different scope.
Yeah, it's.
All right, so now that that's reflecting off of the substrate, go ahead and move it a little further onto the substrate just to make sure you get a full reflection.
There you go.
Okay, now on your detector, you're going to need to realign to center.
I don't have a signal reflection anymore. How do I realign to the center?
So if you remove your detector, you should see a spot on your screen reflecting
Oh,
off
okay.
of.
You want to reflect this to the substrate. Got it. Okay. a second.
Yes, you're reflecting off of the substrate back to the detector, but you've got to realign the detector.
Okay, yes. Now I'm gonna, yeah, I see that. I'm realign the detector so I capture. So basically we're bouncing the laser off the chip or substrate, God, and then
Correct.
realign the detector to that signal.
Okay. I see your sum signal is extremely low. It should be higher.
I am
there
not.
We go.
Yeah, okay. And center it. Good.
Okay, open your signal versus time window.
Let's trace, retrace.
Directly to your right. The one with the T. So on the top left of your screen, Song, underneath environment, see the T? Yeah.
There you go. Yeah.
Signal versus time. And what we're looking for is we're looking for multiple channels. We want to see raw deflection and sum. So change one of them to deflection. Add another channel. And set that one to sum.
And make it big. There you go.
All right, now start acquiring data. Just hit the blue button.
Should I do a longer time, not 10 seconds, like 1,000 seconds?
Yeah, go for as long as you can.
Okay. Yeah.
I think it'll only get up to 15 minutes.
All right, sample rate, 10 hertz, 50 hertz, 10 hertz is good.
Oh, 10 hertz is fine.
Okay.
And just let it start acquiring data.
Cool.
And what you'll notice is the data is drifting. So we'll need to let it acquire for a little bit. But see how it's rescaling?
Yep.
So your raw deflection is climbing right now. The reason why your raw deflection is climbing is because your detector is still moving. After you realigned it and readjusted it, the screws that you use to align it with have backlash in them. So it's always important that whenever you align your detector, if you're rotating the detector, say moving the dot from left to right, as soon as you got the dot as far right as you want it to, backtrack just a little bit to remove some of that that backlash that's settling in the screws. So this is just known as mechanical drift. You'll see that your sum signal is still staying relatively stable, but that deflection signal is still moving.
Yeah,
and right now,
the reason you want to put on the substrate is because that is a very stable signal source, right? There's no thermal.
Correct. There's nothing interfering with the signal.
Okay.
So you know that this is real mechanical drift that you're seeing. And we're only at 90 seconds and we've already got, what is that, 30 millimeters or 30 millivolts of drift in that signal.
And it eventually will settle down, right? Because
yes, it will eventually settle down, but this could be an indicator that you've got something else going on with the system as well. Mechanical parts wear out just like anything else mechanical. If your detector is really, really loose, this can be a real problem for you. And what can wind up happening is your detector could, kind of just release pressure all at once and cause you to crash into your sample. So it's important to take care of your detector. There should be some O-rings in there that keep things nice and tight and keep things aligned.
Cool.
So my goal is when I'm working on these systems, I don't want to see that raw deflection drift more than 35 millivolts over a 15-minute period. And you're already well beyond that.
Yeah, this is a very old detector. This detector has a very odd, strange mechanical design I never seen. The little legs poked out. So yeah, probably a 15-year-old. It's probably more than that. 20-year-old.
I think I know what detector you're talking about. Has a little handle on the side of it.
Right. Yes. Yeah.
I don't know why they didn't pursue that design, but anyway. So with this particular detector, what I do is I will align everything and then I will let it settle for about a half an hour before I run my test. After about a half an hour, I'll run it and see if it stays within that 35 millivolts, and that lets me know if the detector is stable or not.
Interesting.
But from your perspective, and you're doing force curves and you're doing all of these other different measurements, you're talking about how these topography is acquired and how deflection is acquired. You can see how this drift can cause problems in your image. So always make sure that you've allowed your system to stabilize before you try and do anything critical, I guess.
Yes, the raw deflection signal, as we see, this will be coupled into the baseline of your force curve. Basically, the force curve baseline will going up or going down, and then if image in a very fine-tuned force set point, it's going to couple into the force. And as the deflection goes up and up, the force will go lower and lower until tip of the sample lose contact. If we image in liquid, imaging air, that's kind of rough. That it probably doesn't matter.
One of the things that I'm noticing as well is your sum signal is slowly drifting down. You see that?
Yes.
What's happening there is actually electronic. That has to do with your laser source. Depending on the model scanner you have, I believe yours is a low coherent 3-wire laser, correct?
Yes, that's correct. Yeah.
That's a constant power laser. And the electronics, what they're trying to do is they're trying to maintain the power output of the detector by altering the current. So it's varying the current applied to the diode. And that's why you see your sum signal kind of moving around a little bit, because if you can imagine a laser that is less efficient is going to require more current. And any laser that requires more current is going to generate more heat. More heat makes it less efficient. So if it becomes less efficient, it tries to apply more current, and more current creates more heat, making it less efficient. And it goes into what we call thermal runaway. So that's why a lot of the lasers that we've seen historically have a finite life that's completely unpredictable. We don't know how long a laser can last. So it can last years, it can last months. You just never know with these lasers. So we fine tune these lasers to operate at a very, very low output based on their spec sheets and their capabilities to get the longest life possible. But what you're seeing on your sum signal is the laser's slowly becoming less efficient as it kind of thermally stabilizes.
Yeah, so positive feedback at this point.
And that's pretty much it for detector drift. Just understand there are mechanical drifts, there are thermal drifts in these systems, and you've got to let them settle in order to get the best imaging capable.
Cool. Yes, good, great, thanks.
The motors are a lot more fun to talk about, but that's a long conversation.
I have kind of very strange motor problems that it does not approach to the middle. It's always too short. I've seen it approach too short, and one is always over approach a little bit. Yeah.
How much time do we have left? Are we about the top of the hour?
Yes, we are done today, and people staying around is you can leave or stay around, but I'll be here another 30 minutes or so, just in case someone will have a question to ask me.
Hey guys, it's Jason here. I just have a quick question that I've noticed with my AFM system, and I think it's more with when I'm imaging something on mica, I always find that it seems to be over approaching. And so I've looked at maybe slowing down the stepper motor rate. I don't know if there's any other things that I can give a try.
And you're using the Pico SPM system, correct?
Yeah.
Which scanner are you using?
The medium scanner.
So the 30 micron AFM.
Yeah.
It sounds to me like you need to clean your gears.
In the gears.
Well, not necessarily the gear, the screw threads on your plungers. It sounds like you need to clean those.
Right. That's just that back one there. Okay.
It doesn't hurt to do the front two as well, depending on how old your system is and how much use they get. But they don't have significant impact as long as you give them enough time to settle. But yeah, the back one would be the tricky one to get to.
And so that's, yeah, I've taken that out before. And of course, whatever grease was in there, it's, you know, all dirty and stuff over time.
Yep.
I clean that out and put some fresh stuff. What kind of grease do you recommend?
White lithium.
The white lithium. Okay.
Yep. Your basic auto supplies.
Yeah.
You can just go up to Ace Hardware or one of those stores and just pick up a very small amount.
Yeah.
I will say don't use too much. Okay. A little bit goes a long way.
Yeah.
But if you use too much grease, that just causes more problems with drift.
Right. That's interesting with the drift. I've never actually looked at what you just demonstrated here today. That's pretty cool. Nice demonstration.
Hopefully we can talk about the motors soon, because those ones are definitely interesting.
Yeah.
Let's do the motors next week then.
Yeah, we can talk about them next week.
Yeah, I have to decide. I may have some kind of traveling happening, so yes, I will notify everybody. Can we talk about motors? What kind of preparation you want me to do on my site, Steve?
So for the motor experiment, we don't really need a scanner. We just need you to be able to show the microscope itself with your camera.
Okay.
So you'll need to be able to take one of the covers off and look at the brass cogs and look kind of closely at the assembly so that people will understand what I'm talking about. And sorry, Jason, this is purely for the 5500. It's not for the SPM. But the 5500 motor approach setup is a pretty interesting topic.
So I'm going to put a head on my table and then point the camera from over my head downwards. This is the best view. We're just gonna
the GoPro approach, right?
Yeah, GoPro. I'm just I have to have set up the tripod so it's very tall and point down. And this it's a fun setup. It's gonna be the camera has to be cantilevered and put over my head. And the other side, I need to put a heavy bag so it's actually balanced that cantilever.
But yeah, as long as you can get a camera to focus in on the motor assemblies, we'll be able to go through what's actually happening during the approach and withdraw and why we see so many issues with that approach process.
Okay, let's do that and then record it, put on online. This is another topics. Lot of the old instrument had those kind of problems. When you do AFM, it's not obvious, but when we do STM with a small scanner, and yeah, it's a problem become more obvious.
Yeah. And just for, since we're on the topic, just so everybody knows, you had talked about the motor step size in the software and changing the step size.
Step size, okay.
Don't think that the step size is accurate. It's not. It's not even close.
Yeah, so let me share this again. Let me show you what we're talking about here. Motor. There you go. Is that travel you're talking about, right? 0.26 micron.
That 0.26 micron, and there's also another one where you can control step size as well. Either way, like your withdraw distance, right now you have it set to 9999.
Yes.
Both that distance and your travel step motor size, which is the 0.26, both of those, don't count on those being accurate. They're not.
When you say that, are you talking about how many order of magnitude or 0.1? What are we talking about?
I don't know the exact error,
Okay.
but because every single system is different, it has to do with the way that they're built and designed. Just understand that those numbers that are in those two particular categories are for reference only. They are not accurate.
Okay.
So if you say you want to withdraw 100 nanometers, it doesn't necessarily mean it's going to be 100 nanometers. It might be 50, it might be 200.
Okay. Well, this is an interesting topic because I was actually trying to build a STM, and then when I try to build an STM for a client, I would shift to the piezo approach instead of using motor approach, because with a small STM scanner, if we can control precisely approach distance very precisely. That's very important because people do a very strange experiment depend on that kind of thing. Yeah.
Yeah, piezo approach would be a good topic to do as well.
Yeah. Okay, let me stop sharing again and come back to this computer.